In computational theory, especially when we analyze algorithms and complexity, we need a formal and consistent way to describe the input to a problem. Encoding is the process of representing a problem instance, the input to a computational problem, as a string of symbols so that it can be processed by a machine. For example, a Turing machine or an actual computer. Let us say we use a set of symbols E to encode an instance of a decision problem P, and we call this encoding scheme E. The set E star represents all possible strings formed using the symbols in E, including the empty string epsilon. Now the question is, do all these possible strings represent an instance of P? The answer is no. There may be some strings which will not be an encoding of any instance of P. Since P is a decision problem, there will be a subset of valid strings that encode instances of P with the answer no, and a subset of strings that encode instances of P with the answer yes. So we can categorize all possible strings into three groups: a subset of strings that are not an encoding of any instance of P, a subset of strings that encode instances of P with the answer yes, and a subset of strings that encode instances of P with the answer no. Let us try to understand this with the example of the traveling salesman problem, where we aim to find a route with the minimum cost. Traveling salesman problem can be represented using adjacency matrix. The traveling salesman problem can be converted into a decision problem by introducing a cost bound k and asking the question, given a list of cities and the distances between every pair and a number k, is there a tour that visits each city exactly once, returns to the starting city, and has a total cost less than or equal to k? Now, let us see how we can encode an instance of the decision version of the traveling salesman problem. First, we write the cost bound as an integer. Then, we write the number of cities as an integer. But if we write the cost bound and the number of cities side by side, one cannot identify them easily. Therefore, we need a separator. Here we use a colon as the separator. Next, we write the rows of the adjacency matrix. The elements in a row are separated by commas, and the rows themselves are separated by semicolons. This way, we can represent an instance of the decision version of the traveling salesman problem in a structured format. For this representation, we need symbols which include digits 0 to 9, a colon, semicolon, and a comma, right? So E is the set of these symbols. E star represents the set of all possible strings using these symbols. Now, let's write a string using these symbols which represents an instance of the decision version of the traveling salesman problem. This is a valid encoding, and this instance is a yes instance because there is only one root in the graph, and the cost of the root is 45, which is less than or equal to k. Next, we write another string using these symbols. This string also represents an instance of the decision version of the traveling salesman problem. However, there is no possible root in the graph that has a cost less than k. Here k is equal to 80. Therefore, this string is a valid encoding of an instance, but the instance is a no instance. Now, let's write another string. This string is not a valid encoding because there are only two entries after the second colon and before the first semicolon, while the number of nodes is 3. If a graph has 3 nodes, the adjacency matrix will be 3 cross 3, and each row will contain 3 elements. Let's take some more strings. In this string, there are 2 colons after 45, which makes it invalid. In this string, there are two semicolons after 15, which makes it invalid. In this string, colons and semicolons are missing, which also makes it invalid. These strings are invalid encodings. They do not represent any instance of the decision problem. Here, we want to show that if we select some symbols to encode an instance of a decision problem where the answer is yes or no, the strings generated using the selected symbols can be categorized into three classes: a set of strings representing yes instances, a set of strings representing no instances, and the remaining strings which are invalid because they do not represent any instance of the problem. In summary, we use a set of symbols E to encode a decision problem P, and we call this the encoding scheme E. E star represents the set of all possible strings that can be formed using the symbols in the set E. These possible strings can be categorized into three groups: strings representing yes instances of decision problem P, strings representing no instances of problem P, and strings that are invalid, meaning they do not represent any instance of the problem. Strings representing yes instances, or in other words, the set of strings that encode instances of decision problem P for which the answer is yes, are known as the language of decision problem PLP. If a result holds for LP, then it holds for the decision problem P under encoding scheme E. This means that the language LP is just another way of representing the decision problem. Once we fix an encoding scheme E, every instance of the problem corresponds to exactly one encoded string. Therefore, proving something about the set of accepted strings is equivalent to proving it about the original decision problem. A problem can be encoded in multiple ways, depending on the rules we use to represent its instances. Let us consider an instance of the traveling salesman problem shown here. In the first encoding scheme, we apply the same rules we discussed earlier. We will refer to this as encoding scheme E1. Under this scheme, the instance is encoded as given here. All strings produced by this encoding that represent yes instances of the problem form what we call the yes language under encoding E1. This collection of strings is referred to as the language of problem P with encoding scheme E1. This completes our first encoding. Now let's encode the same traveling salesman instance using a binary encoding scheme. In this approach, we begin by writing the number of nodes, followed by the rows of the adjacency matrix, and then the cost bound k, all represented in binary. We will call this approach encoding scheme E2. For this particular instance, 4 bits are enough to represent each number. The encoded instance looks like this. Again, all strings in this scheme that represent yes instances belong to the yes language under encoding E2. So we define the language of problem P with encoding scheme E2. This completes our second encoding. This example clearly demonstrates that a single problem can have multiple valid encoding schemes, and each encoding defines a different formal language that represents the same underlying problem. So, there may be different ways to represent or encode a problem. One thing is clear: depending on the encoding scheme, the size of an instance may vary. If we analyze the complexity of a problem using one encoding scheme, our observation should not change drastically when we switch to another encoding scheme. Let us say under one encoding scheme, the input length or size of an instance is x, and under another encoding scheme, the size of the same instance is y. If the size of an instance under one encoding scheme can be expressed as a polynomial function p of the size under the other encoding scheme and vice versa, then we say if there exists an algorithm of polynomial time complexity for the problem using the former encoding, then an algorithm designed using the latter encoding scheme will also have polynomial time complexity. There are many realistic models of computation, such as one-tape Turing machines, multi-tape Turing machines, and random access machines or RAM. These models are polynomially equivalent, meaning that if a problem can be solved in polynomial time on one model, it can also be solved in polynomial time on the others. Our modern computers are also polynomially equivalent to these models. To understand the theory of NP-completeness, we fixed a one-tape Turing machine, also known as a deterministic Turing machine or DTM. What we achieve with one can also be achieved with other realistic models of computation. Deterministic Turing machine or DTM consists of three main components: a tape, which is a two-way infinite sequence of tape squares, each holding a symbol; a finite state control or the brain of the machine; a read-write head that scans and modifies tape symbols. When we write a program or formal specification for a DTM, it must define a finite set of input symbols or input alphabet, a finite set of tape symbols or tape alphabet, which includes all input symbols and a special blank symbol, a finite set of states Q, including a state Q naught and two special halting states Q accept and Q reject, a transition function that specifies for each non-halting state and tape symbol the next state, the symbol to write, and the direction to move the head. left represented by L, right represented by R, and stay represented by S. To demonstrate the working of a Turing machine, we write a DTM program to check if a binary number is even. First, we list a few even numbers along with their binary representations, and then we list a few odd numbers. From this, we can observe that for even numbers, the rightmost bit is 0, and for odd numbers, the rightmost bit is 1. The key idea is that a binary number is even if its last bit is 0. So, what should our DTM program do? It should read the input binary string from left to right. It should move until it reaches the end of the string. Then, it checks the last symbol. If the last bit is 0, the string is accepted. Otherwise, it is rejected. Since the input is a binary string, the input alphabet consists of 0 and 1. The tape alphabet includes input symbols and the blank symbol B. We define four states. Q0, the initial state used to move right through the input. Q1, the state used to check the last digit. Q yes, the accepting state indicating the last bit is 0. Q no, the rejecting state indicating the last bit is 1. There are three possible head movements: L for left, R for right, S for stay. Now, there are six transition functions. Let's look at the first one. If the current state is Q0 and the current symbol or bit read by the head is 0, then the next state remains Q0. The symbol on the tape stays 0, that is no change. The head moves to the right. If this sounds confusing, don't worry, we will understand it clearly with an example. Suppose the input binary string is 1100, which is equivalent to the decimal number 12, an even number. We have defined six transition functions. Initially, the tape contains only blank symbols. We write 1100 on the tape. The initial state is Q0. The head reads the first bit. Current state Q0. Current symbol 1. According to the second transition function, the head writes 1, that is, there is no change. Head stays in state Q0 and moves right. Again, the same transition function works. Now the input symbol is 0 and the state is still Q0. Here, the first transition function applies. The head writes 0, that is, there is no change. Head remains in Q0 and moves right. Again, the first transition function works. Now, the current symbol is the blank symbol B and the state is Q0. Here, the third transition function applies. The head writes B, that is, there is no change. The state changes to Q1 and the head moves left. Now it's time to take a decision. Current state Q1, current symbol 0, that is the last bit of the input. The fourth transition function applies. The head writes 0 or no change. The new state becomes Q yes and the head stays in place. Since the final state is Q yes, the machine accepts the string, meaning the input represents an even number. Although we demonstrated the working of a DTM for a very simple task, trust me, it can perform any operation that a normal computer can, though it would be extremely slow. For example, the instruction set of a computer includes fundamental operations like reading from memory, adding the contents of two registers, incrementing the value of a register, and so on. A DTM is fully capable of implementing these fundamental operations. The tape of the DTM can serve as memory and registers that store binary information. We explain the DTM because it forms the basis for understanding time complexity and the complexity classes of problems, which we are about to define next. A DTM program M with input symbol sigma accepts an input string x belonging to sigma star if and only if it halts in the state qaccept. The language LM recognized by the program M is the set of all strings in sigma star that M accepts. For the remaining strings, that is sigma star minus LM, the DTM may or may not halt. However, when we talk about the notion of an algorithm, the DTM must halt on all input strings. In this video, we explored encoding and the role of the computational model. It's important to understand that when we discuss the complexity of a problem, our conclusion should not depend on the specific encoding scheme or computational model used. Why? Because all reasonable encoding schemes are equivalent with respect to polynomial time complexity, and all realistic computational models, such as Turing machines, RAM models, and others, are also equivalent up to polynomial time. However, to rigorously analyze the complexity of a problem, we need to fix a specific but reasonable encoding scheme and a realistic computational model. This allows us to formally define the decision problem and determine its membership in a complexity class. In short, to define the complexity class of a problem, we must first fix both an encoding scheme and a computational model. In the next episode, we will dive into the P class and the NP class, exploring what makes problems easy or hard to solve and why that distinction matters. Thanks for watching. Don't forget to like, share, and subscribe so you never miss what's coming next.